This is the first installment of Physiology Raw, Real, Authentic, Without Cuts with Wyatt Peterson. This is answering question 1 of exam 1 for the essay questions. So I got the question set up so I could read it. It says define homeostasis. Homeostasis is the body's tendency to go towards a stable equilibrium. And an example of this, and then including in this discussion the components of reflex control pathways. Reflex control pathways involve afferent and then efferent pathways. So afferent is a receptor sending a stimulate or sending a signal to a control center, which is usually the brain, right? Control center. And so the efferent is going to be the control sending a signal back to the affected area. So I'm just going to put receptor, but it's really the affected area. So an example of this is if you're feeling hot, feeling warm, so the receptor saying it's too hot, and then the control center saying let's do something about it, so it's going to cool it down. So you can see vasodilation, maybe even a sweat gland, stimulating the sweat gland, so you start sweating, you start cooling down. And then the next part kind of plays into this. It says explain negative and positive feedback loops and give some examples. So like it says, there's two feedback loops, the negative and then the positive. So negative is going back, you're just going to the set point. This is usually what we want. And the positive, sometimes we need this, is going away. Going away. Let's go away from set point. Alright, so the one that we discussed in class is blood pressure going down. So what we will see in that usually is a vasoconstriction and then like heart rate or something that goes up. And so in the negative feedback loop, we're going to see these two things. Got a little graph here. See these two things, and it starts going down because of the blood pressure going down. We're losing blood volume or something. These things will activate and it'll go back up. So that's a negative feedback loop right there. And then sometimes it'll keep going down even though it's doing these things. So this is an inadequate negative feedback loop, which is a bad situation. Sometimes if we have a fever, so now instead of blood pressure, we're talking about body temperature. So if the body gets sick, it's starting to fight an infection, the body will establish a new set point. So this is a new set point. And so like anything that we do to achieve this new set point is still negative because it's going towards a set point. Like I said earlier, positive is just going away from a set point. So now that is part 1. Part 2 of the essay, describe the 3 types of protein-mediated transport discussed in class. So let me just erase this, set the stage. Gotta be careful about erasing. I don't want to knock down my phone. Knock down my recording apparatus. Just the phone. Alright, so the 3 types of protein-mediated transports. We got diffusion through channels. Diffusion through channels. So we're gonna make a cell here, make N big out here, and then so sodium's big out here, like a high concentration, low concentration. So diffusion through channels, we got a little protein channel, because usually sodium is impermeable to the cell, so it can't go that way. So it'll go, when a channel's open, it'll go through here, and it'll be able to get into the cell and pursue that equilibrium, get equal concentration gradients. Because they always want to go down their concentration gradients. Then we got carrier mediated diffusion. All right, so that's going to be so we got another cell here. Then we're going to put a little protein right here. But this one's going to be a little different because it's usually going to be closed. Let's see if I can draw good. Geez. Okay, there's a big old protein right here. So now Na is big out here, or I guess it doesn't really matter, but we'll just stick with sodium. So Na wants to go in, so it's going to bind to these little pockets right here. And since it's bound, it's going to make a conformational change in the protein. So now the protein might flip. So it's going to take those sodiums, put them on the inside of the cell, and so now they're able to disassociate and go into the cell that way. That's carrier mediated diffusion. And then there's the active transporters. So there's two types of this. The primary. That's right. Primary. Classic example of this protein action. Na is big on the outside. Sodium is big on highly concentrated on the outside, and then sodium is not so concentrated on the inside. So naturally, it wants to go in, but it won't. Same thing with K. It's not as concentrated on the inside, but highly concentrated. Low concentration. Can you see that still? Low concentration on the outside, high concentration on the inside. So it's going to use some ATP, going to affect this protein right here. So it's going to work against the chemical gradient to push this one out and pull this one in. So active transport works against chemical gradients. So that's primary, right? So using ATP directly, and then there's this secondary one. So we got a cell, Na highly concentrated outside, Na low concentrated on the inside. So this one really wants to go in, but it can't. And let's see, we'll use calcium because calcium's going to be low concentrated. Well, I guess we could just high concentrated on the inside, then low concentration on the outside. So what we're going to do, so this protein is going to have a binding site for sodium and a binding site for calcium. So calcium wants to leave, but it's going to use the driving force, the driving force of sodium to get pumped inside of the cell again. So this is working against its gradient, but it's using the chemical gradient of sodium to get inside. And then so this is a symport, and then there's like antiport, which is just this opposite. So it'll use the driving force of a different ion to pump outside of the cell instead. So yeah, so that is the active transport. So address the concept of specificity, rates, energy sources involved, competition, saturation, direction. So the ATP would be an example of energy sources involved. Saturation is a little something. So for like, I guess secondary, let me clean this up a little bit. Yeah, so no, let me use this one as an example for, no, stick with the primary. Primary is classic. So with saturation, for this protein to work, I think it needs 3 and 2. So 3 sodiums and 2 potassiums. And so if the system is highly saturated with sodiums, so if it's highly saturated with all 3, the rate is going to be really fast as the protein can work, and it'll just keep going. But say that it only has like a lot of sodiums, so it's like saturated with sodiums. Once potassium runs out, it'll stop working, or once ATP runs out, it'll stop working. And so this is like an example of a really specific protein. And same with usually the channels are very specific with the kind of ions that we'll get in. So it'll use things like hydration, so like the water molecules around sodium, to make sure that only sodiums get in. And so since only one sodium at a time could go through, the rate will be constant, even if this out here is very highly saturated, because it's kind of like a rides at a carnival. If there's a ton of rides, everybody's going to be able to go through and just keep going on the rides, and they won't have to stop. But if there's not a lot of rides, or if there's a ton of people, the rate's going to slow down because it's so saturated. So I think that is pretty much all I got to say on question 1. So welcome to Physiology Raw. Real, authentic, without cuts with Wyatt Peterson. Right, this is the second installment. We're going to be exam 1, question 2. That's what we'll be answering today. I have it set up so I could read it. Explain the process of osmosis. So osmosis is the diffusion of water through a water permeable membrane. This is a water permeable membrane. So ions and other particles can't get through it. So what water wants to do is it'll go towards higher concentrated ion solutions. Osmosis. So part of this is when you start putting stuff into water, osmolarity and molarity come into question. Molarity. So osmolarity is the idea that some compounds, some molecules will dissociate. So a good example is sodium chloride. Outside of water, they're put together, but inside of water, it'll dissociate and start floating away from each other. So if you put 1 mole of sodium chloride into water, it'll become 2 osmolarity because they dissociate. But if you put glucose or other compounds that can't disassociate into a solution, it'll stay 1 osmolarity. Molarity is it doesn't take into account this dissociation factor. So you could put 1 molarity of sodium chloride into a solution. It's 1 molarity, but to describe it more, you would call it 2 osmolarity because that's how it interacts with water. And so that's all I got to say about that first little part. Now it asks to explain how osmolarity and tonicity differ. Okay, so osmolarity is comparing 2 separate solutions. For this, we'll use a solution and then a cell. So there's 3 different types. You could be hyper, hypo, or iso, hypo, and hyper. Yeah, so for example, these two solutions, this solution and this cell is going to be isoosmotic. If we take a particle out of the solution, then this solution becomes hypoosmotic compared to the cell. And then if we look at the cell is hyperosmotic compared to the solution. Tonicity, let me get a better color. Tonicity, it takes into account what happens when we introduce the cell into the solution. So now if we have a solution with these 4 particles and the cell with the 4 particles, is going to be the isotonic solution. And the question specifically asks, how can a solution be isoosmotic and yet be hypotonic to a cell? So for this, I'm going to change the situation a little bit. So this solution still has 4 particles, but these 2 particles are going to be dextrose or just other things that are permeable to cell membrane. While the purple, like these ones right here, are going to be something like sodium that is not permeable. So I'll switch this up a little bit. So now we got dextrose in the question went away. All right. So now, because there's a higher concentration of glucose outside of the cell, some of this glucose is or dextrose is gonna come inside of the cell. So that will turn this into something that looks like. Now it has a red on the inside, red on the outside. Boom, because it's dextrose is permeable to the cell. What happened here is now the solution is hypotonic to the cell. And actually, in this case, with dextrose, the cell metabolizes the dextrose and it'll go away. And eventually, even more dextrose will go inside of the cell, getting metabolized. So now we're left with a very hypotonic solution when compared to the cell. And this will cause the cell to swell because more water will want to go inside of the cell, but that's the next level. So that's how something could be isoosmotic but hypotonic, because it has to take into consideration permeability of the different particles inside of the solution. Moving right along here. So part 2, explain how the resting membrane potential of a cell is established. So, resting membrane. Oops, that's weird. So this will use the same logic we used before with some things that are permeable and some things that aren't. Right? Yeah, so a big example of this is sodium. Even though it's very highly concentrated outside of the cell, it cannot go inside of the cell without special permission, I guess you could call it. But it just can't go in. It's not permeable. But potassium is permeable, and it will go down its chemical gradient. So because of this, so since RMP has to do with, what properties, characteristics of the cell membrane account for the resting membrane potential development? Okay, yeah. I'm gonna make this a little bigger. So when we're adding things to a solution, we never add just straight up sodium. It's always something, it's always a, you know, sodium chloride or potassium chloride. So now we're going to have this membrane, and it's going to be K permeable, K plus permeable. So when we're going to add a bunch of sodium chloride, potassium, actually just potassium chloride. Let's go see into here. So now we have disassociated potassiums and chlorides floating around inside here. And so since there's such a high concentration of potassium, it's going to start to cross the membrane and come over here. And now that we've left, this will go away. So now there's a higher concentration of negative ions. So this will start developing a negative charge on this side. And this will start developing a positive charge on this side. So as it goes down, it's a chemical gradient. It'll develop an electro gradient. And that is that's how a resting membrane potential is formed, because now there's a difference in charge on either side. And so, eventually there'll be enough K's over here, or I guess this one will stay. So every time, the higher concentration of K's will keep driving K over here, but this negative will attract the positive charge of the potassium back over. So it establishes a new equilibrium using the chemical electro gradient. Electrochemical? Chemical electro? Yeah. To move forward, so what properties, characteristics of the cell membrane account for the resting membrane potential development? So like a property would be of a membrane being semi-permeable. Write that down. Semi-permeable. Semi-permeable, or like selective permeability. And then also, these channels also will affect it. So channels, and that plays into permeability as well. So those are some characteristics of the cell membrane that will affect the resting potential's development. What conditions or factors affect the resting membrane potential's magnitude? So an example would be like an action potential. So once an action potential is reached, a sodium voltage gate, so this will open, for a split second. Sodium will rush in, increasing. So instead of negative, this will go up to a positive charge inside of the cell. And so what conditions and factors? So like hitting an action potential is something that will affect the resting membrane potential, or the magnitude of the charge inside. Also, I could imagine other things play a factor. Let me think. Yeah, sometimes temperature. So if a high temperature, proteins will move faster, and so like the inactivation gate of the sodium voltage gate, if it acts faster, it'll close faster, so that will affect its deal as well. All right, moving right along. So the last part of the question says, what conditions? Briefly include a brief discussion of Nernst equation and driving force. All right. Nernst equation is like negative 60, not 16, negative 61, there's like log concentration in, out. So Nernst equation will give us a number to describe how bad, or not how bad, but describe the chemical gradient. I guess I don't like to say it, but it'll describe how bad a ion wants to either leave or get into the across a membrane. So that will give us a number. It doesn't really take into consideration permeability and electrical gradient. It's just chemical gradient, and it gives us a number to describe that. Driving force does take into consideration the electro gradient, right? So so like sodium is a good example because since it's not permeable and it really wants to get into the cell, it kind of shows where the cell is and where it wants to be, and it gives us a number. So like driving force is equal to the voltage of the cell minus the Nernst value that's given out of this equation. Yeah. So yeah, driving force takes into account permeability and takes account. I'm gonna write it down. Sorry, I feel like permeability and the electro gradient. Well, this one, it's just thinking about, kind of just talking about chemical gradients. And it does not talk about permeability, like doesn't really care for permeability. It just is going to give us a number to show how bad that cell wants to move. Or the ion wants to move. And I think that is all I have to say about that. No, I think I misspoke actually. So this does have permeability. Permeability is kind of like the strength. It's kind of equal to the strength of the ion. Well, so this number is going to give us like the desire of the ion. Permeability is a strength. And so with this, since it's not permeable, it shows where the ion is and where it wants to be. So that will give us a number for that. So where the ion is compared to where it wants to be. It gives us a value to show that. Welcome to the third installment of Physiology Raw, Real, Authentic, Without Cuts with Wyatt Peterson. We're talking about action potentials. Essay question number 3 for the first exam. I got the question set up so I can read it and know what it's talking about. So I think for this, discuss the action potential, list its characteristics, describe the events that take place during the typical action potential, including a description of the various phases. I think the easiest way to do that is draw a little diagram of our little graph. So usually the cell that we're talking about is going to sit at 70 millivolts. And then there's going to be a threshold represented by this dotted line. So it's going to be like more positive up this way and more negative down this way for the membrane. And so usually, as the cell is sitting at homeostasis, I'm going to see a little bit just like that, and then as either mechanical or maybe temperature or ligand gated channels open, it's going to introduce more and more positive positive ions into the cell through the cell wall. So we're going to see the stuff go up, right? And then once it passes, if it gets to the threshold, once it passes, it'll shoot way up. And we'll go into a little bit more of the what's going on exactly, but with ion gated, or with the different channels and the different gates that it's waiting for and whatnot. So once it passes threshold, it depolarizes completely, and then it'll start, once it gets to a certain point, or after a certain amount of time, it'll repolarize going down, and then we'll get to a hyperpolarization, and then back up to homeostasis at that 70 millivolts. So this is like a little diagram of the action potential, what it looks like. For each phase, describe the action of the channels involved in the ion's currents. So purple at the yeah, I guess just for continuity. So we got purple right here. It's going to be just normal situation going on. There's the normal amount of potassium leak channels going on. We have that sodium potassium ATP ACE channel pumping its thing. And so for some reason, some kind of stimulant comes along, and we have some kind of mechanical. Should I do this? I'll do it up here. Mechanical or ligand gated channels. Channels are opening, allowing more positive ions into cell. So this could usually, like, sodium is doing that, and so if it's going on, but if it doesn't get to the threshold, then it'll just go back down like normal. But if it does get to threshold, then we see a voltage gated and a channel will open. So I'll draw a little diagram of the membrane so we can kind of visualize what's going on. Let me just make a border for myself right here. There you go. So here is part of the cell. We'll call this extracellular and then intracellular. So we got a protein like this, and then there's this little coil action going on, and then there's a door, and then like a ball chain deal right here. So this is getting pushed down. This is pushed down by positive charges on the outside of the cell. And so if we see that enough positives go in here, there's enough in here, then we'll see that this gate will then, because this is a sodium gate, so if enough positives go in here, this gate will open up. Oh geez, yeah, okay, let me put this on the other side. This gate will now open, letting in a bunch of sodiums into the cell. And so right when this opens, it's just like a time, and then this ball chain, this inactivation gate, so this is active gate, activation gate. This inactivation gate will come in and close it back up. So now the sodium can no longer run into the cell, right? And so that's what we see with this green going on. Is once this closes up, then potassium voltage gated, so K plus voltage gated channels will open. So what potassium does now, let's just draw a little. Potassium wants to go out of the cell, and that in turn will make the cell more negative. And so it goes negative, and then it even gets to the point where it goes hyper negative, or like hyperpolarized. So like shoots down, and then those will close back up because you know that the positive charge inside of the cell goes away. And so finally we're left with, so like hyperpolarization. Can you even see that? Yellow to back to homeostasis. So it goes back up to that 70. Yeah, let me just read the question. So yes, that's the various phases. So homeostasis, some kind of stimuli opening up, putting some positive, opening up channels, putting more positive ions inside. Threshold is met. Sodium channels are open, and they quickly close from the ball and chain, or you know the inactivation gate will close it back up. Sodium or potassium voltage gated channels will open to repolarize down into hyperpolarizing, and then as the sodium potassium pumps and the normal amount of potassium leak channels open up, then it will reestablish its homeostasis. And so with that, there's a few refractory periods. So refractory means that no more, like it can't achieve this action potential anymore. And so we have a time where it's the absolute refractory, meaning no action potentials are possible. So I imagine it's when the potassium voltage gated channels are open, and it doesn't matter how much positive charge or how much sodium you put into the cell, it will not achieve an action potential again. And then there's the relative refractory, where if it's probably be in this region right here, where if you do put enough sodium back into the cell, even though it's hyperpolarized, it will still reach up to threshold and be able to do an action potential once more. I don't have an eraser. Compare and contrast. So graded potential is this right here. So graded is just a solid travel, a solid depolarization of the cell membrane. And so graded potentials don't always mean activation potential, because this could go back down if it doesn't reach that the threshold, and if not enough sodium or other positively charged ions get into the cell membrane, it'll just go back down and nothing will happen. While the action potential is that it does reach threshold of the cell, and it does go all the way up into the positive. Let me label, maybe be like time right here. That's time, how much time passes. Alright, well, I'm going to erase some of this, clear up some room for the next discussion. Alright, now we're just gonna briefly go over some key concepts to help, rules to regulate action potentials. So capacitance is just, let's see, oops. So this is a little equation for this. Q over V. So capacitance is charges. This is volts, charges over volts, and so we could see on the cell membrane. So this is extra right here. Intra. So there's positives on the outside, negatives on the inside, and they're separated. And so capacitance is basically describing that there is a separation of charges, and there's a certain amount of volts that goes into that. In our case, we use millivolts because it's not that big of a difference. So we have a time constant. That's the next one. Time constant, and that's equal to Rm times Cm. So this is the resistance of the membrane times the capacitance of the membrane. So resistance of the membrane is kind of like, from how I understand it, is if you have a membrane, there's little holes every once in a while. So this is extra, intra. And so if you get like an action potential in this section, so you have positives running through this way, but through these little channels, some of the positives can just leave, and so that means that positive won't go as far as to the next section. So to make this number go up, you need to get rid of these. Get rid of those weak channels using something like myelin, right? So now those channels are gone, and then also since there's like positive charges outside of the cell and negative on the inside, something else that slows down to this sphere of influence is negative charges on the inside of the membrane. So if we're able to, because usually, here's the other side, right? Usually they're all really close together, so you have a lot of negatives. And negative charges will slow down, or not slow down, but stop this sphere of influence from an action potential earlier on in the cell. So if you have less of those, because there's less positive, or there's less interaction between the positive charge and negative charge, this will be able to go further. This one won't be able to go further. So the idea is get negative charges out of the way and don't have your positive charges leak out of the cell. So length constant is another one. Constant, and that's equal to the square root of Rm over Ri. So Rm is this is Rm right here, and then inside, inside is going to be Ri. And so Ri is mostly negatively charged ions / proteins inside of the cytoplasm while RM are like positive leak channels, allowing, so those are like examples, allowing positive charge to leave the cell, thus reducing the sphere of influence of an action potential established earlier on in a neuron is the most likely culprit. So let's see, describe the structure of the chemical synapse. Explain how signals are passed. All right. Oh yeah, so I guess, yeah, well, that's, so length constant is, yeah, basically that. If you reduce Ri, like the internal resistance, you have a longer sphere of influence. If you increase membrane resistance, you'll have a better length, sphere of influence. And then increasing membrane capacitance and membrane resistance will also help your sphere of influence get to the part of the cell it needs to go to. Or, in this case, like the synapse, the presynaptic area, what is that? Presynaptic terminal. And that's where we're going now. So we'll get rid of this. So we can make a little diagram of that. Let's do it with a lot of black, I think. Let's see, so we just do a basic one. So we got we got the cleft right in there. Oops. Post. So describe the structure of the chemical synapse and explain how signals pass from the presynaptic, so here, to there. So how does that happen? How do we get signals across? So let's just say we have the good sphere of influence going, and so that positive charge will open some voltage gated channels. Voltage gated. And so this will let in, I think it's some positive, but I'm pretty sure it's calcium, will get into the cell. And then what I didn't draw, oops, oh jeez, are some vesicles with neurotransmitters in them. These vesicles will have these like wound proteins that connect to the membrane of the presynaptic area, and so these, using the calcium, somehow or another, they kind of they like tighten and make this vesicle mend with the membrane to let out its well, let me use a different color. So the what is it called? The neurotransmitters will be able to get into this space. And so this side will have receptors that are sensitive to this. The receptors will pick up the neurotransmitters, and then that will cause a a depolarization. There it is. A depolarization of this membrane. So, hopefully, for the sake of this example, that'll be enough to cause a sphere of influence and continue that same signal onto the next side. So that's how that, and so like this positive will help make that happen again. With the action potential going up the graded potential. So graded potential going up to threshold, achieving action potential. And so now this neuron will be able to send the same signal as this neuron, but using this synapse. And I think next one we'll get even more into this area, but that's for next time. So that's all I got to say about that. This is the fourth installment of Physiology Raw, Real, Authentic, Without Cuts with Wyatt Peterson. We're going to talk about essay question number 4 of exam 1, and I got it set up so I could read it. So compare and contrast the sympathetic division of the ANS, the parasympathetic division of the ANS, and the somatic nervous system. To that, I'm going to do a little diagram of all those systems put together real quick. So this is going to be the vertebral foramen in here with the spinal cord. Here's the processes coming out of the vertebral body and whatnot. So for the sensory comes out of the dorsal horn. It's going to go up into a dorsal root ganglion and then go to where it needs to go. This is the sensory coming out of the ventral horn. And this one will go straight to where it needs to go. So this is part of the... Let me let that go up here a little bit. So, motor. Sensory. And then here's part of the what is it? Autonomic nervous system. Coming out of the lateral root, it goes into the this sympathetic nerve path, sympathetic nerve ganglion. I think it's sympathetic nerve ganglion. And so this is a myelinated section. Oh, wait. And then that will go to where it needs to go, so ANS. And then so if it's above diaphragm, it'll go to the sympathetic chain. This is sympathetic chain ganglion, right? Sympathetic chain ganglion. And then if it goes below, so below diaphragm, it goes to a collateral chain ganglion. And so that's just another point where this main nerve from the spinal cord will travel down into a different area of synapse and then go to where it needs to go. And there's even a third type that will go. Well, so nerves that go to this one are called the splanchnic nerves, and there's one that even will pass through this without synapsing all the way to the target tissue, which is the adrenal gland, but that's a little bit later. So the ANS, both sides of the ANS with this sympathetic and parasympathetic have 2 neurons, and they have to synapse in a certain, in these little ganglions. And all 3 of these make up a spinal cord. The sensory and the motor are made up of 1 neuron. So the point of origin from the CNS, the sympathetic nervous system comes from the thoracolumbar region, while the parasympathetic hold on, while the parasympathetic comes from the cranial sacral regions. Okay, so continuing on with the questions include such things as their point of origin, check. Number of neurons, check. In the pathway, so check. Yeah, locations of ganglia, so sympathetic chain ganglion, and then collateral chain ganglion. Neurotransmitters, types of receptors and actions. All right, we get to talk about that real quick. So here's a little, let me do a little diagram. So we got our sympathetic, and these aren't to scale because there's a little bit of a size discrepancy. And then we got like a target. I'll just put it all together. Target. Can you see that still? And then there's a sympathetic, which is a special situation for sweat glands, and then we're going to do the parasymp. Right. And we'll just draw these out. So all three of these spaces, all three of these synapses have the acetylcholine for their neurotransmitter. These two have acetylcholine. So I'm just going to ACH. This one has these two as well, right? And then this one has the epinephrine or norepinephrine. Which would be the called adrenergic. I'm gonna just spell it out because I am bad at saying this word. Adrenergic. So this one is the only one that's this, while all these other ones are cholinergic, meaning they have acetylcholine in them. Okay, and it continues types. So the type of receptor in each one is going to be nicotinic, means it's excitable by nicotine. So these, maybe I'll use a different color even. So make a little note, receptor, nicotinic, and these ones are going to be the ionotropic, that meaning they'll release, or when they're activated, they allow sodium to go inside to create a new action potential, so the signal will propagate down the line. There's another one, not depicted, but I'll still write about it. Metabolotropic, and these ones activate G proteins. Then they have a certain mechanism behind that, and that's how they continue sending the signal down. Receptors, actions. Okay, I'm gonna make some more room, and then we're gonna talk about more about this cholinergic and adrenergic receptors and what that means, the subdivisions and whatnot. So let me just erase this. Okay. Let me start with this color. COLINER. receptors. Nicotinic and muscarinic. So cholinergic receptors. They do the they receive acetylcholine, right? And then there's two different types. And this one has a N1, which will be discussed later. This is the neuromuscular junction. And then the N2, which is found, if you remember this diagram over here in between, it's the postsynaptic neuron has it as a receptor. All right. Receptor. And so this one is going to be located in the parasympathetic nervous system. This one has the types of receptors is M1 through M5, so like 1, 2, 3, 4, 5. And so the evens, so the even numbers of M are inhibitory. That means they hyperpolarize. The membrane, so if a receptor gets these, then it's harder for the membrane to go through an action potential. And then the odd ones of M are excitatory. Means they depolarize. So this means they would probably let in sodium into the cytoplasm to depolarize the membrane to allow an action potential to continue with its course. And then so I think that's going to do it for cholinergic. So I'm going to erase this, get some more room. Blue this time. So then there's the adrenergic receptors. And so these ones are alpha and betas. So alpha 1, beta 1, and 3. Then we have alpha 2 and beta 2. So these are, I'm going to use the same word as I used before. Excitatory, and then inhibitory. So these ones, instead of acetylcholine, they'll respond to, oh wait, that's not how you spell that. Norepinephrine, right? And then epinephrine and dopamine. So all three of these are they're made from tyrosine, which that's kind of fun, but that's not important. So these ones will respond to norepinephrine, epinephrine, or dopamine, and then these ones, alpha 1, beta 3, are excitatory. So they'll let they'll lead to depolarization of the membrane, and then these ones will lead to hyperpolarization of the membrane. Let's think. And I think these ones are in the So sympathetic nervous system. Well, the parasympathetic is that acetylcholine, but there's a exception, which are the sweat glands, which the sweat glands don't have these ones as sweat gland neurons. The sweat gland postsynaptic neuron doesn't release these, while the sympathetic postsynaptic neurons do release this. Yeah, except for the sweat glands. They're still part of the sympathetic, but they release acetylcholine instead. So make sure you remember that one. Give mechanisms for actions of each type of receptor. What happens when the... Okay, so I already talked about what happens when the neurotransmitter binds to the receptor. It'll either excite or inhibit. We already talked about that. And I think that we'll have to do. I think it's important to make sure I said for ANS. Let me use, this is a different idea. So let me ANS. So the first neuron, the presynaptic neuron, is myelinated. The post isn't. The postsynaptic neuron isn't myelinated. I think that's all I have to say about that.